Stand in an empty field at midnight, and the world feels solid, serene, predictable. The grass rests where it must, the moon keeps its steady arc, and each breath seems as ordinary as the one before. Yet beneath that hush, reality hums with a very different cadence, one stitched from probabilities rather than certainties, from shimmering possibilities rather than fixed facts. A century ago, physicists fired a thin beam of electrons, particles of matter as familiar as the atoms in your hand, through two narrow slits cut into a metal plate. They expected each electron to choose a single path to land on the screen behind in neat, particle-like clusters. Instead, the screen lit up with a rippling interference pattern, as if every electron had taken both paths at once, then interfered with itself along the way. When the scientists tried to spy on the electron's mid-journey, the pattern collapsed into dull, particle-like dots. As though the act of watching forced each electron to make an irreversible decision, that simple experiment blew a hole clean through classical certainty. It whispered that the universe does not commit to one story until compelled. It hinted at a realm where objects explore countless possibilities in parallel, where measurement is less about reading a pre-written page and more like choosing a single line from a draft filled with alternative endings. Some shrug and call this realm weird, as if the quantum were an optional oddity reserved for particle accelerators and sci-fi plots. But remove quantum rules, and nothing familiar remains. Atoms fall apart. Chemistry loses its periodic rhythm. Stars fail to shine. DNA can't replicate. Every sunrise, every memory, every living cell relies on laws that are, at their root, indeterminate. Consider the emptiest vacuum we can imagine. Even there, fields quiver with zero-point energy, spawning pairs of particles that flash into existence, borrow a moment of reality, then fade. These restless jitters seed the large-scale structure of galaxies and breathe life into every laser pointer, MRI scanner, and smartphone chip. The quantum, in other words, is the operating system. Classical physics is merely the desktop wallpaper, user-friendly, but never the whole machine. Tonight, we begin a journey into that operating system. We'll trace uncertainty not as a flaw in our instruments, but as a principle etched into existence. We'll watch electrons hold two destinies at once, see particles half a universe apart share a single handshake, and learn how the very randomness that unsettled early physicists now powers the encryption that guards your digital life. By the end, you may find comfort or wonder in knowing that every sunrise is the outcome of quantum dice quietly rolling in the dark. The cosmos does not whisper in absolutes. It speaks in chances. And it is precisely those chances that let stars burn, planets form. And as creatures of dust and thought, look back in astonishment at the invisible dice forever tumbling beneath our feet. Picture a dim laboratory in 1909. On one side, an electron gun whispers, releasing charged bullets one at a time. Ahead, two razor-thin slits have been etched into a sheet of metal. Behind them waits a phosphor screen, eager to record each impact. To every classically trained physicist in the room, the prediction is obvious. Each electron must choose left or right, tracing two neat columns of dots, no different from pellets through twin windows in a barn. Their confidence rests on centuries of common sense. Apples fall, planets orbit, bullets fly in single, well-defined paths. Even light tamed by Newton's prisms seemed at worst a curious wave, never both wave and bullet at once. So the double slit is posed as a simple sanity check. Confirm that matter, like marbles, obeys one lane at a time. The first few shots land exactly where expected, bright pinpricks behind each slit. Boredom settles, pipes glow, then hundreds become thousands. Patterns emerge. Faint bands, bright, dark, bright stretch across the screen like ripples on a pond. The electrons are not piling up behind their chosen doors. They're interfering, canceling, reinforcing, as if each one were a spread-out wave exploring two routes simultaneously. Common sense does not crack, it shatters. The experiment whispers a dangerous possibility. Nature does not commit to a single story until forced. Questions sculpt the answers we later record. To test the mystery, the researchers slow the gun. One electron every few seconds, then one per minute. Tiny, indivisible packets hurled through space utterly alone. Still, Over time, the interference fringes bloom with surgical precision. Each solitary electron appears to consult a silent, unseen crowd of its own possibilities before deciding where to land. Confusion ripples outward. If electrons behaved purely as waves, the pattern would make sense, but waves arrive as continuous ripples, not single, staccato flashes. If they behaved purely as particles, the fringes would vanish, leaving two simple piles. Instead, the screen records a truth stranger than either picture alone. Every electron is both, or rather it is something deeper in amplitude of potential paths, collapsing into a single dot only at the instant of detection. Colleagues propose hidden dirt on the slits, stray electric fields, faulty screens. One by one, those excuses die. The result endures across light: electrons, neutrons, even giant carbon-60 molecules, each containing 720 nucleons. Scale up the mass 1,000-fold, and quantum rules still refuse to yield. The universe seems to insist. Superposition. Multiple realities coexisting is not a laboratory fluke. It is the opening move of every interaction, from starlight striking your retina to atoms forging life's first proteins. And so the double-slit reveals its ultimate lesson. Reality holds its breath in overlapping drafts, till observation pins a single version to the page. If a lone electron can weave two paths at once, perhaps the trick is simple ignorance. So physicists add tiny detectors, microscopic flashbulbs, just behind each slit. Their mission: announce, unambiguously, left or right. The moment the detectors click, the interference fringes vanish. The screen fills with two mundane blobs, as if the electron suddenly remembers it must behave like a classical pellet. But watch closely. The detectors are whispered quiet, drawing almost no energy. They don't jostle the electron the way a hammer startles a bell. Instead, their mere availability to record which path information erases the wave of possibilities. Observation isn't a nudge, it's a negotiation. Once the universe delivers the answer, it deletes every alternative draft. Turn the detectors off, and the fringes return like ghost handwriting under lemon juice. Reality, it seems, is not filmed in secret and replayed later. It is written in the act of asking. To make sense of this, physicists embrace a radical rewrite. Particles do not carry precise trajectories until measured. Instead, each possesses a wave function, a mathematical melody that assigns an amplitude to every possible path. Add two amplitudes, and they can reinforce or cancel, just like overlapping ripples on a pond. Yet the wave function is not a material ripple. It lives in abstract space, predicting probabilities, not certainties. Only when a detector fires does one possibility crystallize, its likelihood given by the square of the amplitude. Born's rule. This shift reframes reality. The universe is less a clockwork and more a vast decision tree. Branches weighted by probability until observation prunes all but one. Between emission and detection, the electron isn't smeared matter, it is potential, an ensemble of futures humming in superposition, and this isn't limited to subatomic realms. In photosynthesis, excitons explore many molecular routes simultaneously, choosing the most efficient path to drive life's energy economy. Your phone's semiconductor logic relies on electron waves tunneling through barriers no classical object could cross. The double-slit, then, is not a curiosity, it's a Rosetta Stone. It teaches us to read the language of amplitudes, interference, and collapse, a dialect spoken by every atom and echoed in every ray of starlight. The skeptic's last refuge is scale. Perhaps superposition only rules the realm of the truly tiny. So experimenters upsize the test subjects. First come neutrons, 2,000 times heavier than electrons, still drawing crisp interference fringes. Then atoms, clusters of protons, neutrons, electrons marching together as a single quantum wave. The patterns persist. In 1999, researchers at Vienna load a beam with football-sized cages of 60 carbon atoms, buckyballs. Each molecule is a miniature geodesic dome, 1 billion times heavier than a photon. One by one, they glide through to nanoscopic slits. Hours later, the detector screen blooms with a familiar zebra-striped signature. Even this molecular giant travels every available path at once until forced to decide. Today, the record stands at organic compounds of hundreds of atoms. Each behaves like a programmable probability cloud. The boundary between quantum and classical is not particle size, it is isolation. Shield a system from stray gas molecules, thermal jostling, and starlight, and superposition scales upward with eerie ease. The lesson is unsettling. Your desk, your heartbeat, the moon herself would exhibit the same interference. Were they not incessantly measured by trillions of environmental collisions? Quantum isn't small, it is simply shy, vanishing when the world looks on too closely. What if reality could be cornered by timing? Physicist John Wheeler proposes a twist. Decide after a particle passes the slits whether to reveal which path it took. In the laboratory, photons enter a Mach-Zehnder interferometer. 2 arms, 2 mirrors. At the last instant, a movable beam splitter either recombines the paths, inviting interference, or removes the possibility, recording which route. Astonishingly, the photon's earlier behavior conforms to the future choice. If the splitter is present, interference appears, as though the particle always traveled both routes. Remove it, and the photon seems to have picked a single arm all along. The decision made nanoseconds late rewrites the past description without violating causality. Probabilities were never locked until information became available. Push further. The quantum eraser stores which path data on an entangled partner photon. Erase that information after detection, and the interference fringes revive in retroactive clarity. It is not that events travel backward in time, but that nature withholds commitment until every shard of potential knowledge is settled. These delayed choice experiments close the loophole of hidden trajectories. The universe does not keep a secret ledger of definite histories. Instead, events exist as overlapping drafts that finalize only when the web of information, present and potential, snaps shut. Close the lab door, and the pattern doesn't stay behind. It follows you into every technology, every cell, every star. Your laptop's processor works only because electron waves interfere inside silicon, tunneling through barriers that classical charge could never cross. Lasers exploit coherent superpositions of photon states. MRI scanners read quantum spin, echoes in the hydrogen of your body. Look to biology. In the leaf of a fern, excitons born from sunlight explore countless molecular routes simultaneously. Then interfere to select the most efficient path. Nature's quantum optimization routine. In birds, entangled electron pairs inside cryptogram proteins may let them sense Earth's magnetic field, guiding migrations that paint half the globe in wings. Even the night sky carries quantum fingerprints. Fusion in the sun depends on proton tunneling. Without it, our star would be a cold orb of hydrogen, cosmic structure itself galaxies, clusters. The web of dark matter originated from quantum jitters in the infant universe, later stretched by inflation. Thus, the double slit is not a parlor trick. It is a master key revealing that probability amplitudes underpin chemistry, life, and cosmology. Quantum mechanics is not an exotic overlay. It is the operating code beneath the desktop of classical appearances. Understanding that code is how we build qubits, fault-tolerant sensors, and perhaps one day warp drives of calculation rather than motion. Interference tells us nature holds many options in reserve. But it doesn't explain why those options can never be sharpened into perfect certainty. Measure a particle's position with finer and finer resolution, and its momentum begins to blur. Pin down its energy, and the timing of events smears outward. These trade-offs are not experimental clumsiness. They're woven into the fabric of existence. In Part 2, we meet Heisenberg's uncertainty principle. Often misread as a nuisance, but actually is a pillar that prevents atoms from imploding and sets the minimum hum of every quantum field. We will descend into zero-point energy, watch vacuum fluctuations pop particles into being, and see how uncertainty rescues stars from gravitational collapse, while setting the very noise floor of reality. The double slit showed us that possibilities interfere. Uncertainty will show us why possibilities must remain fuzzy until the very act of being is complete. Together they declare, the quantum is not optional, it is compulsory, creative, and inescapable. Join me as we turn the page from shimmering fringes to the restless heartbeat of indeterminacy itself.